Hey everyone, welcome back, and today let's solve Leetcode problem 790 titled Domino and Tromino tiling. So we have two types of tiles, a 2x1 domino shape and a Tromino shape, and we may rotate these shapes. So the domino tile is just a straightforward 2x1 shape, whereas the Tromino is consisting of three unique units or squares, if you will, in that kind of Tromino shape, and we're allowed to rotate these tiles in any way that we'd like. So we're given an integer n, and we want to return the number of ways to tile a 2 by n board. And since that answer may be very large, we want to return it modulo by 10 to the 9th power plus 7. I think that's just a really large prime number. Nothing too special about that specifically. So in a tiling, every square must be covered by a tile, and two tilings are different if and only if there are two four-directionally adjacent cells on the board, such that exactly one of the tilings has both squares that are occupied by a tile. So to kind of put that into context and really understand what that means, let's just go ahead and look at how the examples are really shaped here. So in example 1, we have n to be 3. Now let's recall what n to be 3 really means. If n is 3, the problem is basically asking us in this example the number of ways to tile a 2 by 3 board. And again, we have to tile it where every square is covered by a tile, and we only can use these two different tiles, if you will, in whatever rotation that we want to. Right, so in this case we have 5 because as our output, because 5 is the number of different ways we can actually tile this completely, right? And if you look, we have a few different options at each step when we're trying to tile this entire board, if you will, right? We could initially just start with the domino facing vertically like this, and the first two examples, and then just use dominoes horizontally or both vertically to finish it off. Or we could rather start with two dominoes horizontally and finish it with one domino at the end vertically. Or we could just use pure Trominos, and if we were to do that, we could either start with this rotation or with this rotation, and these are all the different choices we have to finish fully, kind of completely tile the board, right? So as you can see, again, we have several options. Our options consist of either we can have the domino being horizontal or vertical at each iteration, as long as that's a valid move to make if we have enough space. Or we could pick the Tromino in each iteration to also be horizontal or vertical. In fact, I can't really say horizontal or vertical because of how the way it's shaped, but rather I'll just say one up or one down. And what I really mean by that is if the one singular tile is on the higher row, if you will, or if the one singular tile is facing downward like we see here. Right? That's kind of like our different options of positions we can position our different domino or trominos to be based on each iteration. Now, what does that kind of sound like when we have different choices to kind of place our two different choiced options for tiles? Well, that's DFS. Now, we'll get into why DFS doesn't particularly work for this problem in a few minutes here. Let's just go ahead and look at example 2 real quick. Example 2, n is 1. Well, we really only have one way to do it when n is 1. This is also actually a base case here because when we have a 2 by 1 domino, or rather a 2 by 1 tile, we know we're going to have exactly 2 rows. The only way we can do it is just using one domino. We don't really have another option. Each row is just consisting of one singular block. All we can do is just have a vertical domino and we're done, right? There's no other possible way we could do that without exceeding the space or just straight up without actually fully tiling it in time. So for the constraints here, we see that n is going to be between 1 and 1,000. And so I believe we'd likely get a TLE if we did use DFS, but more importantly, it's not the most efficient solution to this problem, and we'll get into really why that is once we actually talk about the main observations that we really need to make. And the first observation is that for very small values of n, yes, I agree, we can just count the tiling combinations manually, right? These can also be considered as base cases like we saw in example 2. And even honestly in example 1 as well, right? Because when we know n is 0, there's only one way to have an empty board. When we know we have n to be 1, there's only one way to have one vertical domino. When n is 2, there's only two ways. We have either two vertical dominoes or two horizontal dominoes. When n is 3, there's actually 5 different ways like we saw in example 1. We can have 3 domino only or 2 tromino only kind of ways to fully tile it. Now that's fine when we have really small n. So if n was between like 1 and 9, I would say 100% that we can go for a DFS solution here and just go through every single possible choice of which tile to use and which orientation in each iteration to fully tile it eventually. But in this case, since n is rather large, at least relatively for DFS and backtracking standards, we're going to have to efficiently, make this optimize our solution. Right, because as we actually go up, as our n increases, the number of combinations and choices we can make, it starts growing very quickly, exponentially, if you will. And so how are we going to solve that in alternative? It's kind of like a brother to backtracking, but in a more efficient solution. It is dynamic programming. Right, that's how we're going to solve this problem in the most efficient solution using an extra dynamic programming memory array. Right, where effectively the whole purpose of our dynamic programming array that we're going to initialize is that dp at I, it's going to store the different number of ways, and I'll comment this out at the end here, to fully tile a 2 by I board. 2 by I board. And one really key thing here is that we're guaranteed that we're always going to have 2 rows because it's always 2 by n as our parameter input. And that makes this a lot more straightforward as well to easily implement that dynamic programming solution. So that's also a very key kind of factor or observation to really note here, right? And what is that kind of like that key recurrence that we really need to make to help put this into context and actually make this work? Well, dp at any index I, it'd be dp at I minus 1. Plus dp at I minus 2 plus 2 times the sum of dp at index 0 to dp at index I minus 3, right? Now, let me actually quickly type that out and I'll explain it as I go. And we know, again, we just defined what dp at I means, and that can actually be calculated by dp at I minus 1, add that with dp at I minus 2, and then we have to actually multiply 2 times the sum of dp at index 0 up until, or rather, to dp at index I minus 3. Now let's kind of signify what this really means before we actually kind of simplify it, right? Effectively, again, this is to fully tile a 2 by I board at every single index I in the dp array. So dp at index I has that same definition, where effectively to fully, or rather build a full tiling of I, we can use dp at I minus 1, which would basically be the choice of placing a vertical domino at the end, or we could do dp at I minus 2. That's still using only dominoes, but placing instead 2 horizontal dominoes at the end. Or we could have 2 times dp at I minus 3. Why I minus 3? Because then we're going to be using the Tromino. It's going to be that L-shaped kind of 3 square shape, and we can place it as our last option in 2 different ways, in 2 mirrored ways rather, with the different orientations like we saw in example 1. We could either place it like this or like this if you pay attention to my cursor, and so that's why we're multiplying it by 2 to get the 2 different mirrored ways rather than just one orientation for all those different indices, right? And now, this is kind of like that main equation that we're going to have to follow to actually build our dp array for every single index I to get it eventually up until n. And let me just quickly comment these 2 lines out because, of course, these aren't actually part of our solution, at least not formally, right? And effectively, last few things to kind of just go over the high-level solution, rundown of the solution. Of course, we're going to be using that auxiliary memory, that dp array. That's going to have size n plus 1 to actually store the number of ways to tile up to each length. And we're going to, of course, initialize a modulus value as well. That's just really because the problem tells us that, and we want to avoid integer overflow or data overflow if we have really large n values. And so that mod is going to be 10 to the 9th power plus 7. But we're really just going to initialize that as a very straightforward integer, right? So that's the first thing that we're going to do in our solution here. Let me just call it, I'll capitalize it just to kind of differentiate it and make it a little bit better to see. I'm going to call it mod, and it's going to be 10 to the 9th power plus 7, right? Again, this is really just standard practice typically used in competitive programming when we have, rather large inputs, at least for the context of this problem, to avoid integer overflow and keep our answers within 32-bit limits, so we don't get a memory limit exceeded. So yeah, that's the whole point of this mod. Now let's actually quickly take care of our base cases, just to kind of avoid unnecessary quick manual able calculations. So what do we kind of cover as our base case? Well, what if n is 0? We know if n is 0, just immediately return 1. The only way we can actually tile a 2 by 0 board is by doing effectively nothing. There's only one way to tile it, by having an empty board, right? So we just return 1. That's the only way we can do it. And similar logic for n equals 1. If n equals 1, the only way we can do that is actually place that 1 vertical domino for the 2 rows that we have, each of 1 square. And so that's also just only one way of 1. And finally, for our last base case, if n is 2, just return 2. the only two ways we can do it is two vertical dominoes or two horizontal dominoes that each have two rows of each two lengths or 2 units, and so we return 2. And now let's actually initialize that DP array, assuming that we haven't actually hit any of these base cases in all the test cases that we reached line 13. So once we actually take care of the base cases, let's initialize the DP array. It's going to be initialized to all zeros. Sorry about that. My keyboard is not working. All zeros, and it's going to have a size or dimensions of n plus 1, right? Again, n is again the number of columns that we actually have, right? We're initializing this DP with n plus 1 zeros. We're again, DP at index I is going to store nothing but the number of ways to tile up to a 2 by I board, right? And now let's actually take care of the base cases when we actually initialize our DP array here. And this is kind of going with the initial base cases that we covered from lines 7 to 12, if you will. So DP at 0 is going to be initialized to 1. Sorry. DP at 1 is going to also very similarly be initialized to 1, and DP at 2, like we saw in the base case here, is going to be initialized to 2, right? We saw this again on lines 6 through 12 here. This is just to actually build our base cases manually in the DP array, so we can build off of them from there for future I values and for larger n values for the inputs, right? Because, of course, we can just set the known base cases manually in the DP array, where again, 0, 1, and 2, for when n could be 0, 1, or 2, is corresponding to the number of different ways that we build off from there for larger input values and for larger I values, if you will. So now let's actually begin the main kind of iteration and the main building line of our DP array. This is actually the main kind of solution and logic of our code here. So let's actually start building our array. And we're going to do this using a for loop here for I in the range, starting from 3 up until n, technically up until n, but since for loops in Python are exclusive for the second parameter, we're going to go up until n plus 1 exclusive. We're just really up until n, right? Where for each index I in this range, we're going to compute DP at index I using previous values to actually get the number of different ways in total using the previous built values up until then to get the total number of unique ways to get to fully tile this 2 by I board, right? So in this range here, let's have that main calculation here. And again, it's kind of just going to be a simplified version of this, if you will. And the way that's going to work is DP at I is going to be updated to the kind of total sum of all the different choices that we have. What were the different choices that we had? Well, let's kind of just recall them. It's going to be 2 times DP at I minus 1, and that's going to be summed with DP at I minus 3. But very importantly, we don't want to forget to actually mod our answer so we don't have integer overflow in each iteration that we update every index I in the range from. And so we're going to mod that, or take the modulus by mod, and yeah, that's kind of it for the DP array. Now, let's really kind of break down all the different parts and calculations of this line here to really get and accurately obtain the number of different ways up until this index I to fully tile this 2 by I board, right? So how do we kind of arrive at these different values, right, from what we discussed originally? Well, let's break it down. 2 times DP at I minus 1. That is the first calculation, the first computation, if you will, because of course PEMDAS order of operations does matter. We always do multiplication first. So that is the first kind of order calculation that we do when calculating for this index I. And this is actually going to come from the 2 different main cases that we have. That's also why we have a times 2 here, right? We can either add a vertical domino to DP at I minus 1. Or we can add a Tromino that connects I minus 1 and I minus 2. And since we're dealing with Trominos, we also have to multiply that by 2 because, again, for all Tromino cases, there's always going to be a mirror where we just change it in a different orientation, but still take up the same number of units, or squares, if you will. And so we're always going to have to multiply that by 2 to take care of that Tromino case, right? Again, we can either add a vertical domino to DP at I minus 1, or we can add a Tromino that connects I minus 1 and I minus 2 and mirror that as well. And DP at I minus 3, this final value that we're adding, that's going to be handling the dangling Tromino. That's when you place it in an L shape and it spans 3 tiles, and that's kind of why we have DP at I minus 3. That L shape dangling Tromino, if you will, the dangling Tromino case, you put it in that L shape and it spans 3 tiles, right? And we sum up those 2 different choices together for the total number of ways based on all the different choices that we have, and then mod it by mod to keep it in bounds without kind of avoiding integer overflow, right? And again, we derived this recurrence by basically simplifying the sum of all the previous tilings with Trominos into a constant time form, like we discussed in the comment above here when we were kind of discussing the solution, right? And that's actually basically it for the actual building part of this DP array. Effectively, once this for loop is once it finishes executing, once it terminates, all we have to do is just return DP at n, because n is what we want to return. The number of different ways we can do it is it's going to return the number of ways to tile a 2 by n board, right? That's the whole property of the DP array, and that's exactly what we want our outputs to be and what the problem tells us to do right here. So unless I made any syntax errors here, this should be accepted and there should be a valid solution. So let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So on a high level, again, how we're really solving this problem? Well, effectively, we're taking that original idea of DFS with all the different choices we have and all the different orientations that we have with our 2 different options of tiles to use and bringing that to a dynamic programming using more mathematical counting, if you will. Where effectively we're building the solution from ground up until each index I, up until n, which is going to have our final output stored there on the last index of our DP array. Where effectively, we first initialize that DP array with our base cases of 0, 1, or 2 for our input n value, and then we actually iteratively find or fill out all the DP at index I values for all i's in the range from 3 to n in our iteration on line 18 and 19. Where effectively we're using that recurrence relation to actually avoid any nested summations by expressing all kind of our computations in terms of a few previous states using the different options that we have and the different orientations we have with our different tiles options. Where effectively in the end we simply return DP at n. That's going to be again the number of ways to tile a board of width n with 2 different rows, or 2 by n board, which is effectively what our problem asks. That's the final answer, and hence why we output it. So for the runtime complexity of this solution, we bring it down from an exponential using a DFS solution to a linear solution. It's just big O of n. Why? Because we really just loop from 3 to n, and each step would technically just be a constant time. Like this operation in each iteration would be constant, big O of 1. It wouldn't affect our runtime complexity. And so this really is just a singular pass iteration, if you will, from 3 to n plus 1. And so this is going to be a big O of n, or linear runtime complexity. And for the memory or space complexity, guess what? It's also linear. It's also big O of n. Why? Because we're going to be storing n plus 1 integers in this auxiliary DP array, but that's the only extra data structure that we use. And so straightforwardly, it's a big O of n solution, right? Now, technically, we could, marginally further optimize this to big O of 1 space using only the last 3 values, basically just using integers and updating them in each iteration. That's also just a more efficient dynamic programming variation, but I think this is a little cleaner just in terms of pure code and pure computations, because we're all just using this we're storing all these values purely in one singular data structure that we can always access and always build off of in a more kind of simple way, and in my opinion, a little bit more easy to understand as well. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.